I'll start with a quote from Stephen Wright. Experience is something you don't get until just after you need it. There is so much technical knowledge that one drafting book, one mechanical design, one engineering book is not going to get you where you need to go. There's so much practical experience as well as the hands-on, the just getting into the mix and finding out what works and what doesn't. Using and utilizing your co-workers and in the arena of manufacturing, design, engineering, all of those things cross over and end up kind of in the lap of SolidWorks. That any of the solid modelers, whether you're using Inventor, Fusion 360 on the Autodesk products, the Siemens NX, formerly Unigraphics, and Solid Edge, or PTC Pro Engineer, which is now Creo. They've changed it too many times. Anyway, I want to start off with this is the Kindle version of the Elements of Mechanical Design. This is put out by ASME and James Skakoon. Hopefully I pronounced that right. 2008 is got a little bit of date to it, and so it won't have any information on additive manufacturing, which we're all interested in. We know that it's going to be a part of our future manufacturing processes, but the same basic principles will apply to traditional manufacturing and additive manufacturing and going forward into whatever may come. So I've highlighted a few of these. This is the Kindle version. It was about $10 from Amazon, so I think it's a worthwhile read. I'm going to go through and highlighted several comments. So the less thought and the less knowledge a device requires, the simpler it is. And simplicity is also related directly to cost. The more complicated you get, the more geometry that gets included in the in your part, the more it's going to take to manufacture. Let's see if I jumped over that. What a simple design means is that everyone involved with its production and use sees nothing that looks complicated from his or her own perspective or convention. Complexity is buried and invisible. In other words, there is a hierarchy for knowledge and thought. Each hierarchical level may be intrinsically complex, yet the device remains simple if the complexity resides only within its own level. So we're going to take a look at a slide presentation that I do for the CAM class coming up. So as we look through the entire process, from concept to delivery to end of life, all of those considerations at some point have to be addressed. And you're looking at simplicity is going to be an advantage in machining and manufacturing. It's going to be an advantage in assembly. It's going to be an advantage in customer satisfaction. And then when it comes to the end of life, reuse, recycle. I forgot the other three. Repurpose. I better look that up real quick. Anyway, the 5 R's. We want to utilize those throughout the entire process. Comment on the screw threads. I'm very interested in screw threads, so we'll spend some time with that. Despite their abundant scientific and manufacturing complexity, we specify screw threads and fasteners with the click of a mouse. And sometimes there's reasonable thought goes into it. Sometimes it's just what works. And so the threads and fastening, mechanical fasteners are really something that we need to look into. Alright, so simplicity can be subtle. A good example of keeping things simple is designing symmetry into components. Symmetry may add, and I think it's mentioned in here, may add a little bit of cost. The purpose of symmetry is it's easy to design if you are making left and right parts, and it can be one part. It can be assembled in either direction. Even though there's a little bit more that goes into the manufacturing, you're reducing the overall process. So symmetry in nature is something that we really want to mimic. Let's see, let me move that down a little bit. Too common, oh, I missed that one. Symmetry adds information to the component part, thus adding cost. But if it can be manufactured with only a minor additional cost, but reduces the assembly time, makes replacement parts that much easier to manage, can be used across a wider range, it can often be justified. Let me make sure I didn't skip over that one. Not okay. Oh, there it is. I got lost there for a second. 2 common techniques for keeping things simple deserve specific mention. Purchasing rather than making components. We're going to take a look at several companies that provide a wealth of hardware. Chances are they're making millions of them, or if not thousands, and their cost per unit versus you making something specifically or having it custom made is going to be much cheaper. And then specifying components by standards. So when we look at the standards, the ASME standards, the ANSI application of those standards, things that have already been thought out and are known to work is a good starting point rather than trying to reinvent the proverbial wheel. Everything in design, including independence of function, is a compromise. All right, so they're going to talk about the degrees of freedom and constraints, and we want to look at those compromises with a critical eye. And then seek independence of the function of a device, but do not preclude combining functions within parts. And that is specified or is discussed within the next group. So maybe jumped ahead of there. All right, so lost the independent one. All right. Okay, so they use the function of a locking mechanism, 3 separate handles versus 1 handle, and the constraint is anything that's going to keep it from moving. So constraint, restraining your parts, that you don't want to over constrain. It adds cost and doesn't provide any additional value. You may find that there are times where you want that additional load distribution, you're overcoming tension, compression, those different types of forces in your mechanism. So be aware of the constraint. If you rigidly constrain a component at more places than are needed, you'll start a fight between places. All right, exact constraint means applying just enough constraints to define a position or motion, no more, no less. We're going to deal with constraints in SolidWorks as relations, geometric constraints. There's going to be several definitions that we're going to look at. And it works in the sketches. It also works in our in our assemblies. Okay, so a constraint definition is a point of contact maintained by a nesting force wherein the nesting force vector goes through the contact point and normal to the surface of contact. Basically, we're attaching them, whether it's double-sided sticky tape, super glue, the 1/4-20 socket head cap screw, a pan head screw, a nut and bolt, however you choose to mechanically attach your components, we need those constraints. If you must over-constrain design to increase load carrying or improve stability, you must mitigate that over-constraint with elastic deformation. It has to be able to move. If you make the tolerances too tight, if you have the expectation that it will be made perfectly every time, you will be disappointed. So let's see, there should be one more. Alright, so stiffness or rigidity defines how much something deforms when a load is applied. And then we get into the physics and the material properties. So I would say this goes through part one. I would say get a chance to read. This is a good read. It's not a long book, 98 pages, so the material is a lot of general knowledge that if it never gets said or you've never heard it, then you know, it's valuable information. You'll find in your technical drawing drafting book a lot of this information, maybe not as clearly or specifically stated. You go into the engineering books, you'll find this, but maybe not as specifically stated. Alright, so we'll go into part two later. I'm going to switch over to my CAM introduction, which has tools and tooling, and once we've kind of gone through the process of determining manufacturing, then we'll get into some design.